All right, you guys, so here's the last idea from section 3.3. It's basically a build-up to earlier topic. Let me turn the light on. An earlier topic that we did with regard to the difference quotient. So it turns out that the average rate of change eventually creates the difference quotient, and I'll show you how to do that. Again, we looked at the difference quotient, I think, back in 3.1. We're currently learning about the average rate of change over an interval. So those are the, and then secant lines will come up later. But those are the ideas that we've been working on thus far. But I like to kind of bridge the gap together. Why one is actually the other. So in this one, I've given a function, negative 2x squared minus 3x plus 5, and I'm giving you 5 different intervals where I'm asking you to find the average rate of change of each. So we got a lot of work ahead of us, and that'll kind of motivate the difference quotient. So for the first interval, all right, when I take a look at the difference quotient, again, following our little formula, we got to find the function value at 2 minus the function value at negative 2, and then subtract 2 and negative 2 from each other. So the bottom is obviously 4, but the top, we have to figure out what f of 2 is first, and then f of negative 2. So we're going to come up to the function, and we got negative 2 squared minus 3 times 2 plus 5. I believe that front end will be a negative 8. That'll be a minus 6 plus 5. So I'm getting negative 9 out of that. So this is negative 9, and then we're going to subtract. We got to find the function value at negative 2. So again, doing some work here, plugging that in. 4, I believe this will be a negative 8, positive 6, and plus 5. So 11 take away 8, we end up with a 3. So we get negative 12 over 4. What we get is negative 3. Right? So again, related to our discussion, whatever this graph looks like, this parabola, over the interval negative 2 to 2, it's basically going down on average 3 steps for every 1 over, right? That concept of slope. So again, over this, it's definitely negative and pretty steep. So we're going down pretty quick. So what about the next interval? Well, again, following our little formula, we're going to find the function value at 1 minus the function value at negative 2, and then 1 take away negative 2. Again, the bottom is 3. We've already calculated f of negative 2 as being 3. The only thing we need to do now is find f of 1. So let me come back up here, do some scratch work. I believe we get negative 2 minus 3 plus 5. I'm getting 0 out of that, right? And so we get negative 3 over 3, which tells us we are negative 1. So over that stretch of interval, we are basically going to be equal to negative 1. So again, we're still decreasing, 1 down and 1 over, but not at the same rate that when we had a bigger interval. So we're not going down as fast. And then let's do this one more time because I think you guys are getting the point. But at the next interval, negative 2 to 0, again, following our formula, we have to take f of 0 minus f of negative 2, and we have, 0 minus negative 2. We're going to get a 2 down on the bottom, right? F of 0, when I plug 0 in here, we're going to get a 5. We already know that f of negative 2 is 3. So we end up with 2 over 2, and we end up with 1. All right, so it turns out that over this interval, we stopped decreasing, and we're actually increasing. All right, so pretty incredible there. Again, the average rate of change over that segment. All right, and so I think you guys at this point have the idea, right? Again, to do the negative 2 over negative 1, we would basically just fill in the blanks and do all the labor-intensive stuff. But this is getting a little exhausting. And mathematicians at that time kind of saw the same thing as well. And they said, is there a way we can do this without having to do all these mechanics? And the answer is yes. Okay, so there's your review of the average rate of change. Now let's go take a look at the difference quotient for this function and see what ends up happening. And then I promise I'll put these two ideas together. So the difference quotient. So for the function that we have here, the first thing we have to do from the past is find f of x plus h. So plugging x plus h into my function, we get negative 2 x plus h squared minus 3 times x plus h plus 5. There's a negative 2 there. When we expand this out, this is x squared plus 2xh plus h squared. Distribute that 3, and then plus 5. And so when all said and done, we get negative 2x squared, actually a minus 4xh minus 2h squared minus 3x minus 3h plus 8h plus 5. Right. So there, for the function that's shown, is our f of x plus h. And so the difference quotient, right, we have to put that in there. So we got negative 2x squared minus 4xh minus 2h squared minus 3x minus 3h plus 5. And then we're going to subtract the given function. So negative 2x squared minus 3x plus 5. All of this is over h. So now we have, as we did earlier in 3.1, we have a lot of simplification. So let me drop the parentheses. We have negative 2x squared minus 4xh minus 2h squared minus 3x minus 3h plus 5. Distributing, we get a positive 2x squared, a positive 3x, and a minus 5. And this is all over h. We should see some cancelizations. There's a negative 2x squared and a positive 1. Here's a negative 3x and a positive 3x, and a plus 5 and a minus 5. So when we clean that all up, we have that. And of course, everybody has an h in common. So when we're going to clean this up, what we end up with is negative 4x minus 2h minus 3. All right, so for the function that we've been working with on this page, there's the difference quotient. And you're saying, well, you know, big deal. Well, let's go back, right? How in the world does this help us with what we did up here in the average rate of change? Well, if we take a look, you'll notice a couple of things. Number one, that the left endpoint of each interval is negative 2. So essentially, x, or a, is negative 2. And then what's changing is the h value here, right? The size of the interval is 4. Here, the size of the interval is 3. Here, it was 2. Here, it's 1. And here, it's a half. Well, that length of the length of the interval, that's your h. Okay? So when I put this together, here's our formula. We've already calculated the average rate of change from negative 2 to 2. We did that by hand, but I could actually use this formula that we basically created to do the same thing. All I have to do is plug in x is negative 2, and so again we're going to redo from negative 2 to 2. So the left endpoint is negative 2. The length of the interval is 4, and so when I plug that into this formula, we end up with negative 4 times negative 2 minus 2 times 4 and minus 3. We end up with 8, take away 8 minus 3, and lo and behold, we end up with the same answer that we did when we were doing it the hard way. All right, although I guess that's pretty difficult too. How about, let's check it one more time. So what about the interval from negative 2 to 0? Well, again, x is negative 2. The length of the interval is h, so that's 2. And so when I plug that into the formula, and that's basically what the difference quotient is. It's a formula for the average rate of change. We get 8 minus 4 minus 3. That's 4 minus 3, and lo and behold, we end up with 1. And so with that, without any further ado then, since this is working, rather than finding this out by using the definition like we've been doing, right, what we can do is use the formula where x is equal to negative 2, and in this case h is 1. So when I plug it into the formula that we created down here, we got negative 4 times negative 2 minus 2 times 1 minus 3. That's an 8. That's a minus 2. What we end up is a value of 3. Okay, and then even this last one, right, again, we're going to save us the agony of putting a fraction into the function, what I can do is use that x is -2 and h is 1/2. And so plugging that into our formula that we found down here, this is -4 times -2 minus 3 times 3/2, and then plus 5. We get an 8. I believe that's a -9/2 and plus 5. 8 and 5 is 13. Take away 9/2. This is 26 over 2 minus 9/2. And we end up with a nice looking 6, so like 15 over 2, or what we know to be 7.5. So we can actually calculate the average rate of change using the difference quotient. And then this is actually a toolbox for the derivative that's coming up later on when you guys start taking calculus, whether it's 212 or 220. But we're getting a little lengthy here, so let me just cut to the chase. Again, the big idea is average rate to change over an interval, so I actually calculated that the old way, the definition way. There's the difference quotient idea for a function, and then the thing that I'm trying to connect is that the average rate of change and the difference quotient actually play along with each other. The difference quotient is a formula for the average rate of the change of the function for any interval. And so I can do it for any interval rather than just have a packed one. And again, that'll set up your calculus later. That wraps up 3.3. That's our final thoughts. If you have questions, you better ask and get online. Whatever the case might be, good luck with that quiz, and we'll keep on forging ahead. Talk to you guys later.